Now the key point for you is the duty cycle terminology. It's the length of time expressed as a percentage that a welding machine can operate at its rated output within a 10-minute period. So for 10 minutes, in terms of its rated output, how long can it operate? So for a typical duty cycle for welding machines is normally 60%. So 6 minutes out of 10 is what it can run at its operation time, which means your loading capacity. Automatic continuous welding operations can require a 100% duty cycle, which means they can do 10 minutes of full blast over a 10-minute time. So that's your terminology for duty cycle in terms of what their rated for capabilities are. Another key thing to understand is the actual, is the actual cable size. So for example, my conducting equipment, my electrode here, and my ground cable, which is not a very good job on my part, or they have wires coming out, right? Let me pull up my image here. These wires right here. Notice how small these are in the image. If I can maximize that image a little bit. Notice how small these wires are. In some of the welders you may have seen, these wires can get much larger, and they can get nice and thick. What controls the thickness? Well, there's a couple things. First of all, the amount of amperage or amps that you have flowing that the machine can put out controls what size of conductors you have. Because if you have a lot of amperage, you need bigger and bigger and bigger conductors. Small amounts of amperage do not need large conductors. For example, if you look at speaker wire, that actually has electricity running through it, but the wire itself is very, very small in diameter. But if you look at perhaps the electrical cable behind your stove, or even something a little smaller than that, your refrigerator, those conductors, or the wires going out, are going to be larger. It's because they actually use more amperage. And when amperage goes up, conductor size goes up. Another factor is distance. How far is the equipment machine from the actual electrodes and grounding? How much distance do we have from here to here? That affects them, specifically the size. So for longer distances, even if let's say that you're pulling 50 amps, if you go longer and longer distance, your amperage doesn't increase, but your size of your wire does have to increase to account for the transmission loss and those kind of things. So it's one of the things to keep in mind. Now, wire sizes, in case you're not familiar with them, are referenced as AWG, the American Wire Gauge size, and these numbers are actually a size of a sort of diameter. So you can actually look up these sizes. As an internet search can always find you the data you're looking for. I just did an AWG wire size chart and found this nice little PDF. Let's see if there's a graphic in here somewhere. There we go. So check it out. Your 40 AWG is a very small wire size. Look how big an 18 AWG ends up being. So there's a little bit of difference in some of this stuff. Higher numbers of wire sizes mean smaller size. Your speaker wire has a tendency to be in this general area versus your cables for, let's say, your refrigerator or even larger things. They end up having multiple wires bound together. So you can see the difference between the two. See how this 12 AWG is solid, and then you got a 12 AWG is the same, roughly the same size, but it's stranded with multiple pieces. 10, 8, 6, 2, and 0 AWG is a different size altogether. So they actually move a little bit differently, and you can always look up and find out the actual diameters of these wires versus their AWG wire size. A quick little search will easily find all the charts you need for something like that. So back to our point. So the AWG wire size is the actual standard wire size that we use, numbering system that we use for what size conductors we're going to use. So if I have my electrode, and I'm not drawing it very well, but here's my electrode, and here's my wire going back to my box. If I cross a certain size, I'm going to have a larger wire with my machine, or maybe some cables that have larger wires. Take a look at this chart here. This is a kind of a suggestion or recommended welding size based on the average length amperage and the length. So let's say you're running a machine that runs 75 amps and you have a 50-foot cable. You're probably going to have a number 6 wire. Okay, again, these are AWG sizes. If you're getting up to 100 feet, you're okay. You can still go with a 6. If you go up to 75, you have to step up in size, which means you step down in number. Look how large you have to go. If you have to go to a number 1 if you're going 200 amps and 150 feet. If you're at 50 feet, you can still use a number 2. See how the amps increasing and the distance increasing makes a difference in the overall size of wire you have to use, which kind of makes sense. Obviously, if you increase the amperage, your wire has to go up, but not many people realize that your increasing distance increases the wire size as well. Now, you are going to notice that the AWG has this different convention too. When you see this 1/0, and that's basically when you're getting to a different scale and size wiring, and you can check those out too if you need to learn about them. So let's take a look at the equipment, the setup, and the process, and what's actually going on in Smaw application. So let's start off. You've got your welding machine, obviously, and you've got your lead that goes to your electrode holder. And keep in mind, your electrode is not the part, even though I say it sometimes. I mean, your actual electrode is your consumable right here. Your holder, which holds the electrode, is attached to your wire that's running back in. Then, of course, you've got your other wire coming out, which connects to your workpiece, which of course is your piece of steel, whatever you're using, and it's got a clamp to create that grounding. Now you'll probably, if you've done this before, obviously you probably understand that you sometimes need to clean this connection right here to make sure you get a good solid clamping effect and the electron flow is good. If you have something really, really rusty or painted or that kind of thing and you don't get good current, you're not going to have a good arc, in this case, good flow of electricity or electrons. So you'll notice that in the process, your two parts are being welded. Your area between electrodes and weld parts is the space in between where the arc's occurring. And we've got this little enlarged view of what's going on down here. So we start off. Here's our electrode coming down. We tap it to create and establish the arc and then begin the weld. You can see the shielding effect occurring at this point. So it's the above, the tapping, and then you get going. Once you're there's a scratching process too, where you, instead of doing the straight up and down maneuver, you're doing more of a sway, or more scratch, and you establish the arc and you keep on going. You know, everyone learns this by doing it, you know, the hand actions and that sort of thing, but essentially that's what you've got. At this point in the process, both electrons are ready to go. You know, there's plenty of electrons ready to flow right now in here, and they want to get to here. It's charged and ready. It's not till the point of contact is actually made to get that flow going, get that arc created, and have that essentially continuous arc occurring as it moves along. So here the electrons are flowing freely. In both these two cases here, they're just potentially ready to go once the tap occurs. All right. So there's your basic visual version of the principle. Let's look at the terminology and things that are actually occurring in these processes. All right, so to get started, we begin by setting up our situation. We've got our clamps on and everything, and we actually end up selecting the amount of current or the amount of amperage going from the welding machine through the cables to the electrode holder, and of course your flow there. So this amount of current is based on experience and data in terms of what you may set it to and what procedure you may be doing. And it points out that there's different ranges and that sort of thing, but you will learn that as you get to doing the work. You'll notice that in this application it's talking about adjusting the current, not actually adjusting the voltage. Voltage is pretty much the standard here. I mean, there are some cases where it can change, but for your most of your procedures, you're really just controlling your actual amperage, the amount of current flow through your system. Once you make contact and that electrode touches the metal, you're completing the electrical circuit as we've shown, as we drew it out, and the electricity is flowing from the welding machine into the lead and through the electrical holder, through the electrode, through the air to the welded parts, and that's back to completing the circuit back to the machine. So that's what's happening during the arcing process. The arc length is distance from the electrode to the molten pool of base metal. And of course, obviously, that you learn through experience, you have to keep this constant, and the distance is, the ideal distances. Through experience, you'll get that. Travel speed, of course, is how fast you're moving along in the process, and of course, the angle is of the electrode in relation to the perpendicular line from the weld. So there's your overall procedure. So what we'll actually do is we'll get you a link or two or some videos that you can watch in the process if you're not super familiar, or these are standard training videos that you can check out to see the process in action, which is a lot more interesting than me talking about it. But now that you've seen the process, let's talk about a very important part of it, and that is this little fella right here, the electrode. Because the electrodes are not just one type, they come in a wide variety. So let's take a look at some components to the electrode and kind of what it looks like up close. By the way, to go with some of that terminology, this of course was the electrode, this is your workpiece of course, direction of travel, and your perpendicular line straight up and down off of it. We'll go ahead and tie that into the work angle and the travel angle that you can see here, just so you understand the terminology that we're referring to up above. Okay. Anyway, back to the electrode. So what you see here is actually a nice little visual description of a welding electrode, and we'll talk about the terminology. Here is a visual understanding of what they're showing you there in that image. You can see your conductor and you've got your flux over top. So let's take a look. So your flux covering, which actually gets consumed in the process and the filler gets deposited, your wire of course is your actual metal filler. These things come with a numbering system. So for example, a very common numbering system, or a very common welding rod, is a 6010. I don't think that was on the other one. There are also 6011s. Let's take a picture there of the other ones. So here we go. We've got an E6013. Let's take a look at that image. An E6013, E of course standing for electric, and your 63. Now what do these numbers mean? Well, I'm glad you asked, because here's your understanding. Your flux composition, well, let's talk about strength. Your tensile strength, or what actually we refer to as the strength of the material, the actual metal strength, is 60. And this is of course in KSI. And it is typically, there's a lot of factors that go into that, but if you'll remember, we talked about metals and structural steel, for example, what its strength is. This is in that same category, which means 60 KSI means 60,000. That's what the K stands for. 60,000 psi, or pounds per square inch, in terms of its strength. So this is a very important number, because this means that you want to have this sort of match up with whatever material you're using. So if we're using steel, we definitely want to use something that is close to the same strength as steel, and that's why we use the E60s. Of course, E stands for electric welding, although you see this omitted a lot because it's kind of assumed that's what you're going to be doing. And your welding position, a 1. And of course, that's what we're referring to as our flat overheads, those kind of things, and your flux compositions. So what you want to definitely take away from this is that the rods themselves, the electrodes themselves, their numbering system is important to you in terms of selection. Now most of the time this is going to be called out and given to you instructions, and most of this is pretty standard. But at least understanding what the numbers represent in terms of in the grand scheme of things is important. And understanding what happens to this flux that is used as part of the shielding process. So good little thing there. Take out this chart above, which gives you your classifications. Check it out. So for a 6010 or 6011, which are very, very common, you've got your covering material. It's a high cellulose sodium, the positions you can use with it, and your current that you can actually flow through it. Look what it says, DC. So 6010 is a DC current flow. Notice it didn't say AC. This one does, 6011, which is why 6011s are actually even more common because of that nature. You probably I said 6010s were common, but they're not as common as probably 6011s. Anyway, you'll notice that the covering still keeps a lot of cellulose to it. Got potassium or sodium in these cases, and you can see a variety, pretty much the same positions that are available to them, and AC or DC, DCNs, those kind of things. 6020 is one that you'll probably run into as well, depending on your application. So anyway, a wide variety. These are typically controlled by the designers who are designing the system and the joints themselves. but the terminology is great. So this is a great little graphic to keep handy, put in your workbook, or just pull off the internet and then stores in a nice little handy file, so you can kind of note the composition of the electrode in question. Okay, so we've learned that there are a lot of, well, the process, shield metal arc welding, is actually very economical. Doesn't cost a whole lot in terms of equipment. It's pretty flexible. You just have to have electricity to be where you need to be. And, you know, not super complex. You have your electrode holder, you have your electrode, you have your grounding system, or, you know, your route for the electrons to flow through your plate, and you get your work done. So very economical, very flexible, good to work with, pretty standardized, and obviously used a lot. But there are some disadvantages to Smaw as well. And first of all, one of the things is that while you're welding and you're getting into your groove, you burn through your electrode. So you have to stop and get you another electrode and then keep on going. So there's a discontinuation for long welds that can be a problem, especially if you're in an uncomfortable position or in tight spaces, that sort of thing. Another disadvantage of the process is the slag that is left over that typically has to be removed. In some cases, sometimes it can be used for a protective finish. Well, actually I shouldn't say it that way. What I should say, sometimes it can be left. Most of the time it's going to be cleaned off before a protective finish is added to it, because we don't really want a lot of slag showing up, and you'll see that in cleaning process. And the reason the slag has to come off is because it's actually not really well attached, so it's going to come off on its own. You want it to come off before you add some type of coating or that sort of thing that needs to be locked into place. So the cleanup is a problem with the Smaw process. But all in all, it's one of those type of things you see a lot of people have, and especially if they have a little bit of fabrication or repair operations. An Smaw setup is pretty effective and pretty low cost. All right, so that's a good stopping point for us. We'll throw some links out there that you can watch and some tutorials to see there if you're not super familiar, and we'll call it an episode. See you later.